Have you ever just looked up at the sun and thought, all that energy, why can't we just soak it all up? It's a great question. And it turns out there's this kind of universal speed limit for solar panels. And it's not a technology problem we haven't solved yet. It's a fundamental rule of physics. I mean, think about it. The sun is blasting the Earth with a huge amount of power. We're talking about 1,000 watts for every single square meter. You'd think we could grab most of that, right? But nope. Even our very best, most advanced standard solar cells just hit a wall, and a surprisingly low one at that. So what's going on? What's holding them back? All right, so here's our game plan. We're going to dive into this solar paradox, uncover this universal speed limit, figure out where all that energy is actually going, look at the challenge of actually capturing the electricity, and, this is the cool part, explore the super clever ways scientists are now starting to beat that limit. So let's start with the big one. This isn't about better manufacturing or pure materials. We're talking about a hard theoretical limit. It's a rule that basically says to a standard solar cell, this far and no further. It's written into the laws of physics themselves.
Okay, picture this. It's 1961. Two physicists, William Shockley and Hans-Joachim Queisser, sit down and do the math. They factor in all the ways that energy just has to be lost, the unavoidable stuff. And from that, they calculated the absolute, perfect, you can't do any better than this efficiency for a basic solar cell.
And this is the number they got, 33.16%. That's it. Let that sink in. Out of all the sunlight that hits a theoretically perfect solar cell, the laws of physics say nearly 2/3 of it just has to be lost. But why? And this is what we now call the Shockley-Queisser limit. It's the absolute ceiling for any solar cell made with just a single light-absorbing layer. And the reason it's so fundamental is that it comes from the way light and matter interact at the most basic level. These losses are just baked into the system. So where does most of that energy actually go? Well, the biggest culprit is something you can think of as the Goldilocks problem. And it has everything to do with the color, or really the energy of the sunlight itself.
See, every solar cell material has a minimum energy level it needs to get going. It's called the bandgap. And a photon of light has to have at least that much energy to create any electricity. So, some photons, especially in the infrared part of the spectrum, are just too cold. They don't have enough juice. They fly right through the solar cell like it isn't even there. But then you've got the opposite problem. You have photons that are too hot. Think of bright blue or UV light. They have more than enough energy to knock an electron loose. But here's the kicker. The solar cell can only use a specific chunk of that energy, an amount equal to its bandgap. All that extra energy, it's just wasted. It turns into heat almost instantly. And when you actually break it all down, the numbers are just staggering. That energy lost from the too hot photons alone, it costs us 1/3 of all the sun's power. A full 33%. Add in the 19% from the too cold photons, and you've lost more than half the potential energy before you've even gotten started. Okay, so let's say a photon has the perfect amount of energy. It hits the cell, creates an electron, we're good to go, right? Well, not quite. Now we have to actually collect that energy. And this brings us to what I like to call the leaky bucket problem. You see, when that photon knocks an electron loose, it creates what's called an electron hole pair. Now, to get electricity, we need to grab that electron and guide it out of the cell to do useful work. The problem is, that electron really wants to just fall back into the hole it came from. It's a race against time to collect it before it leaks away. And this process is called radiative recombination, and it's basically the exact reverse of what a solar cell is supposed to do. The electron and hole meet up, and poof, they release their energy as a little flash of light, and the chance to make electricity is gone. Think of it like a two-way street. Anything that's good at absorbing light is, by the laws of physics, also good at emitting it. It's an unavoidable trade-off. And there are a few other little things that chip away at the efficiency too. I mean, the cell is warm, so it radiates a tiny bit of heat away. The voltage you can get out is always just a little bit less than the theoretical maximum, and you can never be perfectly efficient at extracting the power. They're all small, but they add up, and they're all part of that 33% ceiling. So for more than half a century, that 33% limit just seemed like a hard wall, an unbreakable law. But then, scientists and engineers had a brilliant realization. A limit is only a limit if you play by the rules. So they started figuring out how to bend them.
See, the whole Shockley-Queisser limit is built on a few core assumptions. First, that one photon creates exactly one electron. Second, that all that extra energy from hot photons is totally wasted as heat. And third, that you're just using regular old sunlight. The real breakthroughs started happening when scientists looked at these assumptions and asked, well, what if they weren't true? And the most successful strategy so far has been to tackle that Goldilocks problem head on. The idea is simple, but brilliant. If one material can't handle all the different colors of sunlight efficiently, then don't use just one material. This is a multi-junction, or tandem solar cell. It's literally a stack of different solar cells layered on top of each other. The top layer is designed to perfectly capture the high-energy blue light. The light it doesn't catch passes through to the next layer, which is optimized for green and yellow light, and what's left goes to the bottom layer, which is built to capture the red light. It's like a specialized team, where each layer handles the part of the job it's best at. And the results are just, wow. By just adding a second layer, the theoretical limit jumps from 33% all the way to 42%. A third layer, you're looking at a potential 49% efficiency. We're directly fixing the single biggest source of energy loss. It's a game changer.
And this is not just some far-off theory. This is happening right now. In late 2023, a research team created a tandem cell by layering a new wonder material called perovskite right on top of standard silicon. And it hit 33.9% efficiency. For the first time ever, a silicon-based solar cell officially broke the Shockley-Queisser limit.
And that's not the only trick up our sleeve. Scientists are using lenses to concentrate sunlight, which changes the physics a bit. They're working on materials that can take two cold photons and smash them together to make one useful one. There's even research into quantum materials that can use one too hot photon to create multiple electrons. Each one of these ideas is a different way of bending those old rules. So in the end, the Shockley-Queisser limit wasn't really a wall at all. It was more like a benchmark. It was a perfect map of the challenges. By telling us exactly why a simple cell couldn't be perfect, it showed scientists exactly where to innovate, exactly which problems they needed to solve to go further. And it all leads to this incredible question. If a fundamental limit that held for over 60 years can now be broken, what other limits are we going to break next? As we keep finding these clever ways to bend the rules of physics, the true ultimate potential of solar power might be even brighter than any of us can imagine.